Welcome to Calming Cosmos. I'm so glad you're here with us tonight. Before we begin, I'm curious, where are you right now? A quiet bedroom with the lights low, perhaps a comfortable couch, or maybe you're looking up at your own night sky. Wherever you are in this world, you're exactly where you need to be. Find yourself a comfortable position. Let your body sink into the softness beneath you. There's nowhere else you need to be. Nothing else you need to do. If you enjoy these peaceful explorations, a like and subscription really do help this sleepy little channel keep going. And if you're already subscribed, thank you. Truly, your support means more than you might realize. Tonight, we're drifting through one of nature's most elegant phenomena, the cosmic dance of planetary orbits, a ballet that has continued without interruption for billions upon billions of years. As you settle into your bed or your favorite resting place, allow yourself to get completely comfortable, adjusting your pillows, your blankets, finding that perfect position where your body can truly let go. Take a slow breath in and a longer breath out, feeling the weight of the day beginning to lift away. There's no need to stay awake for this journey. No test at the end. No information you must remember. If sleep finds you in the first few minutes, that's exactly what this experience is for. If you drift in and out, hearing fragments of the cosmic story, that too is perfect. We're simply here, together, floating through space and time, exploring the gentle mathematics that keeps our solar system in its eternal dance. Tonight, we're discovering how planets stay in orbit, not through effort or struggle, but through a perfect balance between falling and flying, between attraction and momentum, a balance so precise it has lasted longer than life itself has existed on Earth. This is a story about gravity, about motion, about time measured not in human years, but in the slow turning of worlds, the patient circling of planets, and the quiet harmony of celestial mechanics. So close your eyes, if you haven't already, or let them rest softly open, gazing into the darkness. Feel yourself floating, weightless, as we begin our exploration of the cosmic dance. Gravity, the fundamental force that shapes our universe, is perhaps the most mysterious and yet the most familiar of all natural phenomena. Every moment of your life, you felt its gentle pull, keeping your feet on the ground, giving weight to your body and structure to your world. But gravity is so much more than a force that holds us down. When we think about planets orbiting the sun, we might imagine them as balls on strings, spinning around a central point. But the reality is far more beautiful and far more subtle. Gravity isn't a rope or a chain, or any kind of physical connection. It's a conversation happening across the emptiness of space, a continuous exchange between masses. Every object with mass creates a subtle distortion in the fabric of space itself. Imagine space-time not as empty nothingness, but as a vast cosmic fabric stretching in all directions. When you place a massive object, like our sun, into this fabric, it creates a depression, a gentle curve in the structure of space itself. And this curve, this bending of reality, is what we experience as gravity. The sun, massive beyond comprehension, weighing about 333,000 times more than Earth, creates a profound dimple in space-time. And the planets, each traveling through space, naturally follow the contours of this curved landscape. They're not being pulled in the traditional sense. They're simply following the straightest possible path through curved space. It's like a marble rolling around the edge of a funnel, following the natural shape of the surface beneath it. This bending of space-time, this gravitational well, extends outward from the sun, growing gradually weaker, but never truly reaching zero. Even at the very edge of our solar system, billions of miles away, where the Oort cloud drifts, in the cold darkness, the sun's gravity still reaches out, still curves space, still guides the motion of distant icy bodies. The strength of gravity follows what scientists call the inverse square law, a beautiful piece of mathematics that describes how forces diminish with distance. If you double the distance between two objects, the gravitational force becomes 4 times weaker. Triple the distance, and the force becomes 9 times weaker. This mathematical relationship creates a smooth gradient of gravitational influence, spreading outward like ripples on an infinite pond. For Earth, orbiting about 93 million miles from the Sun, the gravitational pull is just right to keep us circling at a comfortable speed in a stable orbit. For Mars, farther out at about 142 million miles, the pull is weaker and the orbit slower. For Mercury, baking close to the Sun, at only 36 million miles, the gravitational embrace is much stronger and the orbit much faster, racing around the Sun in just 88 Earth days. But gravity isn't only flowing one direction. Every planet, every moon, every asteroid and comet also creates its own gravitational field, its own subtle bending of the cosmic fabric. Earth pulls on the Sun, just as the Sun pulls on Earth. The difference is simply one of scale. The Sun's massive presence dominates the relationship, but Earth's contribution is still there, creating a tiny wobble in the Sun's position that astronomers can measure and even use to detect planets around distant stars. This mutual attraction, this conversation between masses, means that technically speaking, Earth and the Sun don't orbit some fixed point. They both orbit their common center of mass, called the barycenter, a point that lies very close to the Sun's center. Because of the Sun's enormous mass, but not quite at its exact center, the Sun, in its own subtle way, dances too. Gravity also has no speed limit, in the sense that it doesn't wait or travel like a signal. When you move a massive object, the change in its gravitational field propagates outward at the speed of light. This means, if the Sun were to suddenly vanish, we wouldn't know it immediately. Earth would continue orbiting for about 8 minutes, the time it takes for light or gravitational changes to travel from Sun to Earth. Then suddenly, we would fly off into the darkness, following a straight line, no longer bound by the Sun's embrace. But the Sun isn't vanishing. It's been there, shining steadily for about 4.6 billion years, and will continue for billions more. And throughout all this time, its gravity has remained constant and reliable, the steady heartbeat around which all planetary motion revolves. The force of gravity is also incredibly weak compared to other fundamental forces. The electromagnetic force that holds atoms together is about 10 to the 36th power times stronger than gravity. And yet, gravity wins on cosmic scales because it only attracts, never repels, and because it adds up cumulatively. With every particle of mass, a single atom's gravity is negligible. The gravity of countless trillions of atoms gathered into a star becomes overwhelming. This cumulative nature means that the largest objects dominate gravitational relationships. In our solar system, the Sun contains 99.86% of all the mass. Jupiter, the largest planet, accounts for most of the remaining 0.14%. All the other planets, all the moons, asteroids, comets, and dust are merely traces. In comparison, this distribution creates a hierarchy of gravitational influence, with the Sun as the conductor of the cosmic orchestra. Understanding gravity as curved spacetime rather than a mysterious force acting at a distance helps us see why orbits work the way they do. Planets aren't fighting against gravity, trying to escape. They're not held by invisible chains. They're simply following the natural geometry of curved space, like water flowing down a hillside, finding the path of least resistance through the landscape of reality itself. And in this flowing, this endless circulation through curved space, the planets maintain their cosmic dance, neither falling into the sun nor drifting away, but finding that perfect middle path between extremes, a balance we'll explore more deeply as we continue our journey through the mathematics of orbital motion. Before the modern understanding of planetary orbits, people believed that the heavens moved in perfect circles. The circle seemed like the most divine shape, the most perfect form, and surely the cosmos itself would reflect that perfection. But nature, as it often does, had something more subtle and more beautiful in mind. Johannes Kepler, working in the early 1600s, analyzing the precise observations of the astronomer Tycho Brahe, discovered that planets do not orbit in circles. They orbit in ellipses, elongated circles, with the sun positioned not at the center, but at one of two special points called foci. This discovery, known as Kepler's first law, revolutionized our understanding of celestial motion and revealed the true geometry of the cosmic dance. An ellipse has a quality called eccentricity, which measures how elongated it is. A circle has an eccentricity of 0, meaning it's perfectly round. The more elongated an ellipse becomes, the closer its eccentricity approaches 1. Most planetary orbits in our solar system have very low eccentricity, meaning they're almost circular, but not quite. Earth's orbit has an eccentricity of about 0.7, making it very nearly a perfect circle, but with just enough elongation that our distance from the Sun varies by about 3 million miles throughout the year. This elliptical nature means that sometimes we're closer to the Sun and sometimes farther away. When Earth is closest, around early January, we're about 4 million miles away at a point called perihelion. When we're farthest, around early July, we're about 94.5 million miles away at aphelion. Interestingly, this means Earth is actually closest to the Sun during Northern Hemisphere winter, proving that distance alone doesn't determine seasons, but rather the tilt of Earth's axis and the angle at which sunlight strikes our surface. Mercury has the most eccentric orbit of the major planets, with an eccentricity of 0.206. This means Mercury's distance from the Sun varies dramatically from about 29 million miles at perihelion to about 43 million miles at aphelion. This variation creates extreme temperature swings and makes Mercury's orbit a more dramatic ellipse, though still relatively gentle compared to comets, whose orbits can be extremely elongated. Why ellipses and not circles? The answer lies in the specific velocity and direction with which each planet formed. If a planet has exactly the right speed and exactly the right direction, perfectly perpendicular to the Sun's gravitational pull, it could theoretically orbit in a perfect circle. But in the chaotic birth of the solar system, with countless collisions and gravitational interactions, such perfect conditions were virtually impossible. Instead, each planet settled into an ellipse, the natural path for an object under gravitational influence, moving with any velocity that isn't precisely perfect for circular motion. Kepler's second law, sometimes called the law of equal areas, describes how planets speed up and slow down as they orbit. Imagine drawing a line from the Sun to a planet. As the planet moves, this line sweeps out an area of space. Kepler discovered that this line sweeps out equal areas in equal times. This means when a planet is closer to the Sun, near perihelion, it must move faster to sweep the same area as when it's farther away, near aphelion, and moving more slowly. This change in speed isn't arbitrary. It's a natural consequence of the conservation of angular momentum, one of the fundamental principles of physics. Angular momentum depends on both an object's speed and its distance from the center of rotation. As a planet falls closer to the Sun, it speeds up, maintaining the same total angular momentum. As it swings farther away, it slows down, again conserving that precious quantity. Think of an ice skater performing a spin. When they pull their arms in, they spin faster. When they extend their arms, they slow down. The same principle governs planetary motion. The planet isn't choosing to speed up or slow down. It's simply obeying the fundamental conservation laws that govern all motion throughout the universe. For Earth, this variation is subtle. We move at about 18.5 miles per second at our fastest in early January, and about 18.2 miles per second at our slowest in early July. The difference is only about 3 miles per second, barely noticeable in the grand scheme of our year-long journey. But for Mercury, with its eccentric orbit, the speed variation is much more dramatic, ranging from about 38 miles per second at perihelion to about 24 miles per second at aphelion. Kepler's third law describes the relationship between orbital distance and orbital period, the time it takes to complete one orbit. Kepler found that the square of the orbital period is proportional to the cube of the average orbital distance. This sounds complicated, but it simply means that planets farther from the Sun take disproportionately longer to complete their orbits. Mercury, closest to the Sun, orbits in just 88 days. Earth takes 365 days. Mars, about 687 days. Jupiter, nearly 12 years. Saturn, about 29 years. Uranus, 84 years. And Neptune, far out in the cold darkness, takes about 65 years to complete a single circuit around the Sun. Since its discovery in 1846, Neptune has only recently completed its first full orbit that we've observed. This mathematical relationship emerges naturally from the physics of gravity and orbital motion. It's not a rule imposed on the planets. It's a consequence of how gravity weakens with distance and how orbital velocity must change to maintain stable orbits at different distances. Kepler discovered this pattern empirically by studying observations, but Isaac Newton, decades later, showed that it emerges naturally from his law of universal gravitation, proving that Kepler's laws weren't just descriptions, but deep truths about how gravity shapes motion. The elliptical nature of orbits also means that planets experience seasons of gravitational strength. When closer to the Sun, the gravitational pull is stronger. When farther away, it's weaker. But because orbital velocity also changes, these effects balance out, creating stable orbits that neither spiral inward nor drift outward. Over time, some comets have extremely eccentric orbits, with eccentricities approaching 0.99 or even higher. These objects sweep in from the distant reaches of the solar system, where they move incredibly slowly, barely crawling through space. As they fall inward toward the Sun, they accelerate dramatically, whipping around the Sun at tremendous speeds before being flung back out into the darkness, not to return for decades, centuries, or even millennia. Halley's Comet, perhaps the most famous, has an orbital period of about 76 years and an eccentricity of 0.967, making its orbit highly elongated. When farthest from the Sun, beyond Neptune's orbit, it moves at less than 1 kilometer per second. When nearest the Sun, inside the orbit of Venus, it races along at more than 50 kilometers per second, nearly 180,000 miles per hour. These eccentric orbits, these dramatic ellipses, remind us that the cosmic dance isn't always a gentle waltz. Sometimes it's a dramatic sweep across vast distances, a pendulum swing between extremes of speed and distance, heat and cold, light and darkness. And yet, even these wild trajectories follow precise mathematical paths, governed by the same simple laws that guide Earth's almost circular, peaceful orbit. The beauty of Kepler's laws lies in their universality. They apply not just to planets around our Sun, but to any object orbiting any other object anywhere in the universe. Moons orbit planets following the same laws. Planets orbit distant stars in the same elliptical paths. Even binary stars orbiting each other obey these same elegant mathematical relationships. And throughout it all, throughout these ellipses and varying speeds and changing distances, the planets maintain their cosmic rhythm, neither colliding nor escaping, but dancing in patterns that have persisted for billions of years and will continue for billions more, a testament to the stability and harmony encoded in the mathematics of motion. Perhaps the most fascinating question about planetary orbits is why they're stable. Why don't planets slowly spiral inward, falling into the Sun, or gradually drift outward, escaping into interstellar space? The answer lies in a delicate balance between two competing tendencies: falling and flying, attraction and inertia, gravity and momentum. Imagine you're standing at the edge of a cliff and you throw a ball horizontally. The ball immediately begins falling, pulled downward by gravity, but it's also moving forward with the velocity you gave it. The result is a curved path, an arc that eventually brings the ball to the ground. Now imagine throwing the ball faster. It still falls at the same rate, but travels farther horizontally before landing. Throw it faster still, and it goes even farther. Now imagine the ground isn't flat, but curved, like the surface of Earth. If you could throw the ball fast enough, about 5 miles per second, at sea level, something remarkable happens. The ball would still be falling, pulled by gravity toward Earth's center, but Earth's surface would be curving away beneath it at exactly the same rate. The ball would keep falling, but never get any closer to the ground. It would be in orbit. This is the secret of orbital motion. Planets aren't resisting gravity. They're constantly falling toward the sun, but also moving sideways so quickly that they keep missing. They're in perpetual freefall, but freefall in a curved path that circles back on itself, creating a stable orbit. The speed required for this balance depends on distance. Closer to the sun, where gravity is stronger, planets must move faster to avoid falling inward. Farther from the sun, where gravity is weaker, planets can move slower and still maintain orbit. Mercury, racing at nearly 30 miles per second. Earth, traveling at about 18.5 miles per second. Neptune, crawling along at only 3.4 miles per second, each moving at exactly the right speed for its distance from the sun. This balance between falling and flying is called gravitational equilibrium. The inward pull of gravity is exactly matched by the outward tendency of inertia, the planet's desire to continue moving in a straight line. Neither force wins, neither force loses. They exist in perfect balance, creating circular or nearly circular motion. But why doesn't this balance gradually break down? Why don't small perturbations accumulate over time, causing orbits to decay? The answer lies in the conservation of energy and momentum in the vacuum of space. With no air resistance, no friction, nothing to slow them down, planets simply keep moving. The energy they possessed at the solar system's birth remains with them, unchanged throughout the ages. When a planet is slightly perturbed, perhaps by the gravitational tug of another planet, its orbit may change slightly. It might move a bit farther from the sun or a bit closer, but these changes trigger compensating adjustments. If a planet moves closer to the sun, it speeds up, maintaining the balance. If it moves farther away, it slows down. The orbit adjusts itself naturally to maintain equilibrium. This self-correcting nature of orbital mechanics creates remarkable stability. Computer simulations running millions of years into the future show that planetary orbits remain essentially stable over timescales that dwarf human history. Yes, there are small variations, tiny oscillations in orbital parameters, but these changes are bounded, limited, oscillating back and forth, rather than growing without limit. The stability is also protected by angular momentum, which is conserved in isolated systems. Angular momentum depends on mass, velocity, and distance from the center. For a planet orbiting the Sun, angular momentum remains constant unless acted upon by external forces. This conservation prevents planets from simply spiraling inward or drifting outward without cause. Imagine a planet somehow losing orbital velocity. It would begin falling toward the Sun, but as it falls, it also speeds up due to conservation of angular momentum. This increased speed helps it swing around the Sun and back out to its original distance. The orbit becomes more eccentric, more elliptical, but doesn't simply collapse. Conversely, if a planet somehow gained velocity, it would move to a higher orbit, farther from the Sun. But at this greater distance, it would slow down, again conserving angular momentum. The orbit would stabilize at this new altitude, neither continuing to rise nor falling back. These self-correcting mechanisms create what physicists call a stable equilibrium. Small disturbances don't grow. They're automatically counteracted by the natural dynamics of the system. It's like a ball resting at the bottom of a bowl. Push it slightly to the side and it rolls back to the center. Planetary orbits possess this same restorative quality. However, not all orbital arrangements are stable. If planets were too close together, their mutual gravitational interactions could accumulate, causing chaotic behavior, where small changes compound over time, leading to unpredictable and potentially catastrophic changes in orbits. Our solar system appears to have settled into a configuration that avoids these unstable arrangements. The spacing of planets follows a rough pattern, sometimes called the Titius-Bode law, though it's not a fundamental law of physics, but rather an empirical observation. Planets tend to be roughly twice as far from the Sun as the previous planet. This spacing helps ensure that gravitational interactions between planets remain manageable and don't destabilize the system. Jupiter, our solar system's giant, plays a particularly important role in maintaining stability. Its enormous mass dominates gravitational interactions among the outer planets and helps protect the inner solar system from comets and asteroids that might otherwise bombard Earth and the other terrestrial planets. Jupiter's gravity either deflects these objects back to the outer solar system or captures them entirely, adding them to its collection of moons and rings. The absence of massive planets in unstable locations, particularly in the asteroid belt between Mars and Jupiter, also contributes to stability. Had a large planet formed there, its gravitational influence could have disrupted the orbits of both the inner and outer planets, potentially making our solar system far less stable than it actually is. This stability isn't just a happy accident. It's the result of billions of years of gravitational sorting, of natural selection at the scale of worlds. Early in the solar system's history, orbits were likely more chaotic, with planets migrating, asteroids scattered, moons captured and lost. Over time, unstable configurations resolved themselves through collisions, ejections, and gravitational settling until only stable arrangements remained. The orbits we observe today are the survivors of this long process of gravitational evolution. They're stable precisely because unstable orbits didn't persist. They collapsed or ejected or merged, leaving behind only those configurations that could endure the test of deep time. And so the planets continue, circling the sun, year after year, millennium after millennium, era after era, held in balance between falling and flying, between attraction and momentum, neither winning, neither losing, but dancing together in perfect gravitational harmony. The solar system isn't just a collection of independent orbits. It's a gravitationally interconnected system where every planet influences every other planet, and where moons, asteroids, and comets add layers of complexity to the cosmic dance. Some of the most beautiful phenomena arise from these interactions, particularly from what physicists call orbital resonances. A resonance occurs when two orbiting bodies have orbital periods that form a simple ratio. For example, if one moon orbits twice for every single orbit of another moon, they're said to be in a 2-1 resonance. These resonances create repeated gravitational tugs at the same points in the orbits amplifying effects that would otherwise be negligible. Jupiter's moons provide beautiful examples of orbital resonance. 3 of the 4 large Galilean moons, Io, Europa, and Ganymede, exist in a resonance called the Laplace resonance. For every orbit Ganymede completes, Europa completes 2, and Io completes 4. This means the moons return to the same relative configuration on a regular basis, creating predictable patterns of gravitational interaction. This resonance isn't coincidental. It arose naturally over millions of years as the moon's orbits gradually adjusted through a process called orbital migration. When orbits drift into resonance, they tend to lock into that configuration because the repeated gravitational tugs stabilize the relationship. It's like pushing a child's swing at exactly the right moment on each pass, building up the motion rather than disrupting it. These resonances have profound effects. For Io, Jupiter's innermost large moon, the gravitational tugs from Europa and Ganymede combine with Jupiter's own enormous gravity to flex and squeeze Io's interior, generating tremendous heat through tidal friction. This heating makes Io the most volcanically active body in the entire solar system, with hundreds of active volcanoes constantly resurfacing. The moon, Europa, the second moon, experiences similar, though less extreme, tidal heating. This heat is believed to maintain a liquid water ocean beneath Europa's icy crust, making it one of the most promising places in the solar system to search for extraterrestrial life. The energy for this ocean comes ultimately from orbital resonance, from the gravitational dance between moons. Saturn's rings also display beautiful resonances. The rings aren't solid, but composed of countless individual particles, each in its own orbit around Saturn. But Saturn's moons, particularly the small moons, called shepherd moons, create gaps and structures in the rings through gravitational resonances. The Cassini division, the most prominent gap in Saturn's rings, corresponds to a 2:1 resonance with the moon Mimas. Particles in this location orbit Saturn twice. For every orbit of Mimas, the repeated gravitational tugs from Mimas at the same point in their orbits gradually perturb these particles, either pushing them inward or pulling them outward, clearing a gap. The result is the beautiful structure we observe in Saturn's rings a direct manifestation of orbital resonance written in ice and dust. Resonances can also destabilize orbits. The asteroid belt between Mars and Jupiter contains regions called Kirkwood gaps, where very few asteroids are found. These gaps correspond to resonances with Jupiter. Asteroids in these locations experience repeated gravitational kicks from Jupiter that eventually eject them from those orbits. Over millions of years, these regions have been cleared, creating the gaps we observe today. Some asteroids in Jupiter resonances don't escape, but instead are locked into stable patterns. The Trojan asteroids orbit at the same distance as Jupiter, but 60 degrees ahead of or behind the planet at special points called Lagrange points. These positions create a stable balance between the Sun's gravity, Jupiter's gravity, and the asteroid's orbital motion. Thousands of Trojans follow Jupiter's orbit, held in place by this three-body resonance. Earth's moon also participates in the gravitational dance in ways that affect our planet. The moon's gravity creates tides in Earth's oceans, but also, more subtly, in Earth's rock and crust. These tidal interactions transfer angular momentum from Earth's rotation to the moon's orbit. As a result, Earth's rotation is gradually slowing, lengthening our days by about 1.8 milliseconds per century. Simultaneously, the moon is gradually moving away from Earth at about 1.5 inches per year. This process has been ongoing for billions of years. When the moon first formed, likely from debris created by a giant impact, it was much closer to Earth, perhaps only 15,000 miles away, compared to today's 239,000 miles. The day was much shorter then, perhaps only 5 hours long. Over geological time, this tidal interaction has gradually pushed the moon farther away and slowed Earth's rotation to its current comfortable pace. Binary systems, where two stars orbit each other, display even more complex dynamics. Unlike our solar system, where the Sun dominates gravitationally, binary stars have comparable masses, creating orbits where both stars circle their common center of mass. Some binaries orbit so closely that material streams from one star to the other creating spectacular astronomical phenomena. When planets form around binary stars, their orbits must accommodate the complex gravitational field created by two massive objects. Some planets orbit both stars in what's called a circumbinary orbit, experiencing complex variations in gravitational pull as the stars themselves orbit. Other planets orbit just one star in the binary system, with the companion star appearing as an extremely bright point of light in that planet's sky. Multi-planet systems also show complex gravitational interactions. When multiple planets orbit the same star, they gravitationally tug on each other, causing subtle changes in orbital parameters. These interactions can be detected from Earth by carefully measuring the timing of planetary transits or the wobbles they induce in their star. Such measurements have revealed unseen planets in distant solar systems. Some exoplanet systems have configurations that would be unstable in the long term, suggesting they're relatively young, still settling into stable arrangements. Others show tightly packed planets in resonant chains, suggesting ancient, evolved systems where gravitational interactions have sorted the orbits into stable patterns. Gravitational assists, also called slingshot maneuvers, allow spacecraft to change their velocity by flying close to a planet. As the spacecraft approaches, the planet's gravity pulls it forward, accelerating it. As it departs, the gravity pulls back, decelerating it. But because the planet itself is moving, the spacecraft can gain net energy from the interaction, stealing tiny amounts of the planet's orbital momentum. NASA's Voyager spacecraft used gravitational assists from Jupiter and Saturn to reach the outer planets and eventually achieve sufficient velocity to escape the solar system entirely. These maneuvers demonstrate how orbital mechanics can be used creatively, allowing us to reach destinations that would otherwise require impossibly large amounts of fuel. The gravitational dance extends even further. Our entire solar system orbits the center of the Milky Way galaxy, completing one orbit approximately every 225 million years, a period sometimes called a cosmic year. The Sun and planets travel together at about 514,000 miles per hour, held in orbit by the combined gravity of hundreds of billions of stars. and the mysterious dark matter that pervades our galaxy. In this vast galactic orbit, we encounter different regions of the galaxy, experience different radiation environments, and pass through the spiral arms where star formation is most active. Some scientists speculate that these passages through the galactic arms might influence climate or evolutionary history on Earth, though such connections remain speculative. From the smallest moons to the largest galaxies, gravity choreographs an intricate dance, a cosmic ballet where every participant influences every other through the silent language of gravitational attraction, creating patterns, harmonies, and resonances that span the depths of space and the vastness of time. To truly appreciate planetary orbits, we must consider the timescales on which they operate. We measure our lives in years and decades. We mark history in centuries and millennia, but the cosmic dance has continued for 4.6 billion years and will continue for billions more. This perspective, this deep time awareness, transforms our understanding of orbital stability. When the solar system formed from a collapsing cloud of gas and dust, the planets didn't immediately settle into today's orbits. The early solar system was a chaotic place filled with countless planetesimals, asteroid-sized bodies, colliding, merging, and scattering. Planets migrated inward and outward as they gravitationally interacted with the surrounding disk of material. Jupiter and Saturn likely formed farther from the Sun than they are today, and then migrated inward through interactions with the remaining gas. In the protoplanetary disk, this migration could have scattered countless objects throughout the solar system, seeding the asteroid belt and the Kuiper belt with the debris we observe today. Eventually, as the gas dissipated, the planet's orbits stabilized at roughly their current distances. For the first several 100 million years, the inner solar system was bombarded by asteroids and comets. Earth and the other terrestrial planets were repeatedly struck by large impactors. The moon's surface still bears the scars of this late heavy bombardment in the form of vast impact basins, now filled with solidified lava flows that create the dark Maria we see when we gaze at the full moon. During this violent period, orbits were still adjusting. The moon, as we mentioned, was much closer to Earth. The day was much shorter. Mars might have been wetter and warmer. Venus might not yet have experienced the runaway greenhouse effect that created its hellish current conditions. The solar system was young, still finding its equilibrium, but gradually, over hundreds of millions of years, the system settled. The large impactors were mostly cleared away, either colliding with planets or ejected into interstellar space or captured into stable orbits. The planet's migrations slowed and stopped. The orbits reached a configuration that could persist essentially unchanged for billions of years, and persist they have for the last 4 billion years. Earth has circled the Sun approximately 4 billion times, each orbit almost identical to the one before. The same rhythms, the same seasons, the same dance, repeated endlessly. When the first life emerged on Earth, perhaps 3.8 billion years ago, Earth was already in essentially the same orbit it occupies today. When photosynthesis evolved, transforming Earth's atmosphere and filling it with oxygen, Earth continued its patient orbit. When the first animal appeared, when plants colonized the land, when dinosaurs rose and fell, when mammals diversified, when our ancestors first stood upright and gazed at the stars, Earth maintained its cosmic trajectory unchanged, unaware of the dramas unfolding on its surface. This continuity, this stability, is what allowed life to flourish. Imagine if Earth's orbit had been unstable, drifting closer to the Sun or farther away. Over millions of years, the climate would have changed catastrophically. Life might never have gained a foothold, or might have been repeatedly extinguished before intelligence could emerge. Instead, Earth remained in the habitable zone, that region around the Sun where temperatures allow liquid water to exist. This zone extends roughly from Venus's orbit to Mars' orbit, though the exact boundaries depend on many factors, including a planet's atmosphere and geological activity. Earth has stayed comfortably within this zone for billions of years, providing the stable environment that complex life requires. The other planets, too, have maintained their orbits. with remarkable consistency. Mercury, racing around the Sun, has completed about 19 billion orbits since the solar system formed. Venus has completed about 7.4 billion orbits. Mars, about 2.4 billion orbits. Each orbit a repetition of an ancient pattern established in the solar system's distant past. The outer planets move more slowly through their cosmic circuits. Jupiter has completed only about 388 million orbits. Saturn, about 156 million. Uranus, about 55 million. Neptune, only about 28 million orbits. Since the Sun first ignited in nuclear fusion. And yet, even these slower, more stately orbits represent a continuity spanning geological timescales far beyond human comprehension. During all this time, the orbits have remained almost perfectly stable. Computer simulations can model the solar system's dynamics millions of years into the past and millions of years into the future. These simulations show small variations, tiny oscillations in orbital parameters, but these changes are bounded, limited, never growing out of control. Earth's orbit, for example, experiences variations in eccentricity, oscillating between nearly circular and slightly more elliptical over cycles of about 100,000 years. These variations contribute to ice age cycles, affecting how much solar radiation different parts of Earth receive during different seasons, but the variations are small, controlled, predictable. The tilt of Earth's axis also varies between about 22 degrees and 25 degrees over a cycle of about 41,000 years. This variation affects the severity of seasons, the direction Earth's axis points, also precesses like a wobbling top, completing one cycle every 26,000 years. This precession changes which star appears as our North Star and affects which seasons correspond to perihelion and aphelion. These variations, called Milankovitch cycles, were discovered by Serbian scientist Milutin Milankovitch, who showed how they influence Earth's climate. But even these cycles are regular, predictable, and bounded. They don't represent instability, but rather a complex yet orderly set of variations playing out over deep time. Looking forward, we can predict with reasonable confidence that Earth's orbit will remain stable for billions of years to come. Eventually, in about 5 billion years, the Sun will exhaust its hydrogen fuel and begin expanding into a red giant star. At that point, all bets are off. The Sun's outer layers might engulf Mercury and Venus, and possibly even Earth. But until that distant day, our orbit should remain essentially unchanged. The same applies to the other planets, barring some extremely unlikely event, like a rogue planet entering the solar system from interstellar space. The current configuration should persist essentially indefinitely. The dance that began 4.6 billion years ago will continue for billions more, a testament to the inherent stability of gravitational systems that have reached equilibrium. This deep time perspective reveals something profound about the universe. Change on human timescales can seem rapid, dramatic, chaotic, but zoom out to cosmic timescales and patterns emerge. Regularities appear. Stability becomes evident. The universe operates on rhythms far slower than our own, but no less real, no less powerful. Consider the patience of planetary orbits. A single orbit of Neptune takes 165 years, longer than any human lifetime. Yet Neptune has completed 28 million such orbits, each one nearly identical to the last. The repetition is almost beyond imagining. And yet, from Neptune's perspective, if a planet could have a perspective, this is simply existence, the natural state of being. We humans live in the thin slice of time called the present. We experience change, urgency, progression, but the planets exist in a different temporal realm. For them, past and future blur together into an eternal present where the same motion repeats endlessly, neither beginning nor ending, but simply continuing. This continuity connects us to the deep past. The same sun that warmed the dinosaurs warms us today. The same moon that pulled tides over Precambrian seas pulls tides today. The same stars that ancient humans navigated by still shine in the same patterns. We are participants in a cosmic story that extends far before us and will continue far beyond us. And in this participation, there's a strange comfort. The challenges we face, the worries that keep us awake at night, the dramas and difficulties of human life all unfold against the backdrop of this cosmic constancy. The planets continue their ancient dance, indifferent to human concerns, yet somehow reassuring in their reliability. When you look up at the night sky and see Venus shining brilliantly in the twilight, or Mars glowing red near the horizon, or Jupiter bright and steady among the stars, you're seeing worlds that have traced the same paths for longer than life has existed on Earth. You're witnessing a stability, a continuity that transcends all earthly change. This perspective, this deep time awareness, can shift how we see our place in the cosmos. We're not permanent, not eternal, not stable in the way planets are stable. We're ephemeral, transient, brief flickers in the cosmic night, and yet we're also part of the dance. We're made of star stuff, atoms forged in ancient supernovae, assembled briefly into conscious form, able to contemplate the very cosmos that created us. The planets teach us patience. They teach us that the universe operates on timescales that dwarf our own. They teach us that stability can persist even in a dynamic system. They teach us that balance, once achieved, can endure almost indefinitely as you drift towards sleep. Tonight, let this perspective settle over you. The Earth beneath you continues its ancient orbit. The moon pulls gently at the oceans. The planets trace their paths through darkness. All is moving, yet all is stable. All is changing, yet all remains. The cosmic dance continues as it has for billions of years, as it will for billions more, patient, eternal, unchanging, and somehow deeply peaceful. There's something almost meditative about contemplating planetary orbits. Perhaps it's the combination of vast scale and mathematical precision. Perhaps it's the contrast between our brief lives and the eternal circling of worlds. Or perhaps it's simply the beauty of a system so perfectly balanced that it has endured longer than we can truly comprehend. The elegance of orbital mechanics lies in its simplicity, despite the complexity of gravitational interactions, despite the intricate details of elliptical orbits and resonances and perturbations. The fundamental principle remains beautifully simple. Objects Move through curved space, following the straightest possible paths. Mass, curved space. Motion follows curves, and from these simple ingredients emerges the cosmic dance. Isaac Newton, when he first formulated the law of universal gravitation, realized that the same force that pulls an apple to the ground also holds the moon in its orbit. This insight, that earthly gravity and celestial gravity are the same, unified heaven and earth, showing that the cosmos operates by laws we can understand through observation and reason. Albert Einstein took this understanding even deeper, showing that gravity isn't truly a force in the traditional sense, but rather a consequence of curved space-time. Mass and energy curve the fabric of reality itself, and objects simply follow these curves. This geometric picture of gravity reveals the universe as a dynamic, four-dimensional structure where space and time themselves participate in the dance. The mathematics underlying orbital mechanics possesses an aesthetic beauty that mathematicians and physicists have long appreciated. The equations are surprisingly simple, given the complexity of the phenomena they describe. They contain symmetries, conservation laws, and elegant relationships that hint at deeper, fundamental principles governing reality. But you don't need to understand the mathematics to appreciate the wonder of planetary orbits. Simply knowing that the Earth has circled the Sun 4 billion times, essentially unchanged, is enough to inspire awe. Simply recognizing that the same laws govern both the smallest asteroids and the largest galaxies reveals the cosmos as fundamentally unified and comprehensible. This comprehensibility, this accessibility to human understanding is itself remarkable. We might have lived in a universe too chaotic, too random, too complex to permit understanding. Instead, we find ourselves in a cosmos governed by laws elegant enough that we can discover them, powerful enough that they shape everything we observe, and universal enough that they apply everywhere throughout space and time. The planetary orbits also remind us of our connection to the cosmos. We're not outside observers looking in at the universe. We're participants, inhabitants, parts of the system. We orbit the Sun, Just as Mars orbits, just as Jupiter orbits, we're fellow dancers in the cosmic ballet, subject to the same laws that govern all celestial motion. This connection extends deeper than mere physical location. The atoms in your body were forged in stellar cores and scattered across space when those stars exploded. The carbon in your cells, the oxygen you breathe, the calcium in your bones, all were created by nuclear fusion in stars that lived and died before our sun was born. You are, quite literally, star stuff, assembled briefly into conscious form, and you exist on a planet that has orbited a star for billions of years in a galaxy containing hundreds of billions of other stars, most of which likely have their own planets engaged in their own cosmic dances. This perspective can feel simultaneously humbling and empowering. Humbling because it reveals how small we are, how brief our existence, how recent our appearance in cosmic history. But empowering because it shows that we're part of something infinitely larger and more ancient than ourselves. The stability of planetary orbits also offers a metaphor for our own lives. We seek balance between competing forces, between work and rest, between activity and stillness, between connection and solitude. Like a planet in orbit, we're constantly falling and flying, pulled by competing attractions, trying to find that perfect balance where we can sustain our trajectory. Sometimes we drift too close to one attractor, burning ourselves out with too much intensity. Sometimes we drift too far, losing connection, losing purpose, feeling untethered. The art of living, like the art of orbital mechanics, lies in finding and maintaining that balance where we can continue sustainably through time. Of course, the metaphor has limits. We're not planets, predictable and deterministic. We have choice, agency, the ability to change course. But still, there's wisdom in the cosmic example. Stability doesn't mean stasis. The planets are constantly moving, constantly changing position, yet maintaining their overall pattern. Similarly, we can embrace movement and change while maintaining core stability. The patience of planetary orbits also teaches us about the value of long-term thinking in a world that often feels frantic urgent, demanding, immediate response. There's something calming about contemplating processes that unfold over billions of years. Not everything needs to happen quickly. Not every change needs to be dramatic. Earth's orbit changes its eccentricity over 100,000-year cycles. Its axial tilt varies over 41,000 years. Its precession takes 26,000 years. These changes are imperceptible on human timescales, yet they shape ice ages and climate patterns that transform the planet. Slow change can be profound change. As you rest here tonight in the darkness, you're participating in this ancient rhythm. You're orbiting the sun at 18.5 miles per second, covering about 1.6 million miles in a single day. You're spinning with Earth's rotation at about 1,000 miles per hour. At the equator, you're moving with the solar system through the galaxy at 514,000 miles per hour, and you're moving with the galaxy through the universe at nearly 1.3 million miles per hour, and yet you feel still, you feel at rest. This is the nature of motion in the cosmos. Everything is moving, yet everything feels stable. Everything is dancing, yet the dance feels like stillness. This paradox, motion and stillness, change and constancy, is at the heart of existence. The universe is a dynamic system, constantly evolving, yet governed by conservation laws that ensure certain quantities remain forever unchanged. Energy is neither created nor destroyed. Momentum is conserved. Angular momentum persists in this balance between change and conservation, between motion and stability. The cosmos finds its expression, and we, temporary assemblies of ancient atoms, briefly conscious, briefly aware, get to witness this cosmic dance, get to participate in its rhythms, get to contemplate its meaning. There may be no ultimate meaning, no cosmic purpose written in the stars, or there may be meanings we cannot yet comprehend. But there is undeniably beauty. There is elegance. There is harmony. And in recognizing this beauty, we connect with something larger than ourselves, something that transcends our individual existence and links us to the cosmos that gave us birth. As you let go of the day's concerns, as you allow sleep to approach, imagine yourself floating in space, weightless, watching Earth trace its path around the sun. See the moon circling Earth. See Mars glowing red in its wider orbit. See Jupiter, massive and majestic, accompanied by its moons. See Saturn with its rings tilted at an angle, catching the sun's light. All of them moving, all of them dancing, all of them following invisible curves through space, all of them balanced between falling and flying, all of them participants in a ballet that has continued for billions of years and will continue for billions more. You are safe here on this planet. You are held by gravity. You are moving with the earth. You are part of the dance. And as you drift into sleep, the dance continues. The planets continue circling. The cosmos continues evolving. And all is well in the vast, patient, eternal universe. Rest now in this knowledge. Rest in this cosmic perspective. Rest knowing that tomorrow the sun will rise as it has risen 4 billion times before. Rest knowing that the seasons will continue their ancient cycle. Rest knowing that the stars will shine tonight as they've shone for longer than life has existed. The cosmic dance continues. It continued before you were born. It will continue after you're gone. But right now, in this moment, you're part of it. You're orbiting, you're dancing, you're moving through space and time on this beautiful blue world. And that is enough. That is everything. That is the gift of existence in this vast, elegant, endlessly dancing cosmos. Before we end our journey together, if this cosmic exploration has helped you find peace tonight, consider subscribing to Calming Cosmos for more peaceful space content. A gentle like helps others discover these soothing journeys. And if you'd like, share your favorite planet or your thoughts in the comments below. Your support helps us continue creating these restful explorations of the universe. But there's no pressure, no obligation. If sleep has already found you, that's perfect. If you're still drifting, simply rest. The cosmic dance asks nothing of you but your presence. Sleep well. Dear traveler, sleep deeply and peacefully. Let the cosmic rhythms carry you into rest. Let the ancient dance of planets lull you into dreams. There's nothing you need to do, nowhere you need to be. Just rest. The Earth continues its orbit. The moon pulls gently at the tides. The stars shine overhead, and you, safe and warm, can simply let go. Good night, and sleep well in the peaceful, eternal, cosmic dance.